Hello, and welcome to MedEvidence Articles, where we encourage community research and education with weekly articles. I'm your host, Benton Loeyball, and this week we are talking about investigational RNA interference medications. A new way to control high blood pressure. Fruit flies are annoying, and I hate them. It's frustrating because I love fruit, want to have fresh fruit out all the time, and love having the windows and doors open in nice weather. In the past, however, the combination has made the occasional fruit fly outbreak seemingly inevitable. I've tried every solution imaginable: fly paper, traps filled with wine, juice, or vinegar, boiling water in the drains, washing all the fruits and veggies, and so on. To deal with this, I built a fruit box, a small, wooden, screened-in box where we store fruit and root vegetables. This interferes with the ability of fruit flies to get into the box, or, for flies that were inadvertently on the fruit, to get out. It's not foolproof and needs to be emptied and cleaned regularly, but the difference has been overwhelming. This paradigm shift from treating established flies to interfering with their ability to become established is oddly similar to a paradigm shift happening now in blood pressure medications. High blood pressure is as ubiquitous as fruit flies. Around half of American adults have high blood pressure, and it is the leading preventable risk factor for death from heart disease and stroke. High blood pressure is implicated in over 660,000 deaths per year, about the same as the number of people who live in Boston, Massachusetts. Nearly 3/4 of people with a diagnosis of high blood pressure do not have it under control, despite myriad medications available to treat the condition. Unfortunately, for many people, the current medications are little more effective than a vinegar flytrap. Many of these medications target the renin-angiotensin-aldosterone system, abbreviated RAAS. RAAS is a system of hormones in the body that helps regulate blood pressure, fluid balance, and electrolyte levels in the blood. The pathway has a few key molecules and steps, but there are many more pieces doing minor tasks. Key molecules include angiotensinogen, which is the precursor molecule that is ultimately converted into active hormones below; renin, which is the rate-limiting enzyme that determines how quickly angiotensinogen is converted to angiotensin 1. And note that when the body detects low blood pressure, more renin is made, and this system can be corrupted by conditions like type 2 diabetes, which may increase blood pressure. And angiotensin-converting enzyme, or ACE, which converts angiotensin 1 into angiotensin 2, which is biochemically active and raises blood pressure. High levels of angiotensin 2 constrict blood vessels, cause the kidneys to reabsorb more salt and water, and increases levels of other blood pressure-related hormones. Many current blood pressure medications are designed to debug this system. Renin inhibitors like aliskiren target the enzyme renin to slow the conversion of angiotensinogen to angiotensin 1. Angiotensin receptor blockers, or ARBs, like losartan, block the receptors that angiotensin 2 would normally use to raise blood pressure. And angiotensin-converting enzyme inhibitors, or ACE inhibitors, block the conversion from angiotensin 1 to angiotensin 2 and include lisinopril and other medications ending pril. These medications have been effective in clinical trials, but they face challenges as daily oral medications. Doses can be missed, forgotten, burdensome, or come with side effects that may impact consistency. At a more fundamental level, though, these solutions are like trying to hunt down each fruit fly individually. Most medications target a protein. This is great because proteins do things in the body. Proteins include signaling hormones, receptors, structural elements, defense and inflammatory tools, and much more. So targeting them is the most common way to fight a disease. Unfortunately, proteins are relatively large three-dimensional objects that can be hard for medicines to target. This can lead to medications that do not find the protein if it's rotated the wrong way, and medicines that accidentally bind to off-target proteins that happen to have the correct shape. It's like fly paper. You have to just kind of hope the flies happen to run into the paper for it to work, and if you accidentally get your hair in the sticky part, you suffer a pretty aggravating side effect. RNA interference changes the game. While most medications hunt individual proteins like their fruit flies, RNA interference is like building a fruit box. For those of us who haven't reviewed genetics in the last decade or so, RNA is the intermediary step between DNA and proteins. DNA gets transcribed into messenger RNA, which travels to ribosomes to be translated into a protein. This is a necessary step because DNA is long-term storage, while a protein is functional, and the two are made of different molecules, nucleic acids for DNA and RNA, and amino acids for proteins. Interfering with messenger RNA means the intended protein does not get created, stopping the problem earlier in the, quote, life cycle. New medications are being developed in clinical trials to target this messenger RNA. RNA interference offers real potential benefits over traditional medicines. Problem proteins can be stopped more effectively at earlier stages, and specific pieces of messenger RNA code can be targeted, avoiding off-target effects. Another big benefit is that RNA-interfering medications may last much longer than traditional ones, meaning that a daily pill can be replaced with a few injections per year. For a condition like high blood pressure, this would mean much easier adherence and may lead to fewer side effects. With the help of clinical trial specialists and volunteers, we may be able to bring blood pressure under control for hundreds of millions of people. And that doesn't bug me one bit. Thanks for joining us on this week's episode of MedEvidence Articles. If you'd like to know more, all of our sources are linked in the podcast description. You can also visit our website at medevidence.com. MedEvidence provides evidence-based information that empowers individuals to make informed health decisions. We present unbiased clinical research in clear, accessible formats guided by medical experts and provide education for patients and healthcare professionals with a focus on research as a care option. Note that the information provided in this podcast is for general educational, scientific, and informational purposes only and is not intended as and should not be treated as medical or other professional advice for any particular individual or individuals. If you're experiencing any medical issue or have any medical concerns, you should consult a doctor or other medical professional. For more great content, including discussions by physicians and subject matter experts, check out the MedEvidence podcast. My name is Benton, and we'll talk to you next week.